Hi, in this video, I'll be going through another application of differentiation where we learn how to solve optimization problems. So what are optimization problem? Well, the idea is that you have a problem that has some constraints that you can write in terms of equations, mathematical equations, and these mathematical equations, they are related by differential operator. And then what we want to do is, because differentiation allows us to find the maximum and minimum point of an equation, we use this idea to help us optimize, which means to either find the maximum or minimum value of a particular problem. That's what we do. Why is it optimized? Well, it could be because we want to minimize the cost of production. For example, that's one type of problem. Or we want to maximize the profits earned. That's another type of problem. And given the constraints in the question given, we can use differentiation to help us find the maximum and minimum point. We'll take a look at the examples, and by practicing more, you'll get more familiarized with how to convert real life problems into mathematical formulas, which you can then use differentiation to solve. So optimization is really, you just need to go practice, and in this video I'll just show you a few types of problem to get you started with understanding how to use differentiation. So let's begin with the first problem, and this is where we want to find the largest area of our field. So to maximize the area, the equation is x and y. And we know the constraint is that now he's only at 2,400 meters of material for fencing. And so, if we to draw out a picture to visualize, it means that 2x plus y equals to 2,400. And this would mean the x is between 0 to 1,200. And so we need to find the maximum value of x bracket. We sub y now as 2,400 minus 2x on this closed interval. And we just use what we've learned about differentiation and the closed interval method to solve this. And thus, we realize that the maximum value occurs not at the endpoints, but at the critical point at 600. And hence the dimension for the largest area is 600 by 1,200. I hope you can see the general steps to solving it, where we use the closed interval method. What it does is we need to relate. The problem may come with multiple variables, but we are able to substitute the different variables and create one equation in a single variable. And in order to optimize it, we use the closed interval method. And then solve for the absolute maximum value. Another type of problem which can be more interesting is the problem in physics, where we want to show that which point does light traverse, that we want to show that light travels in a medium by a path of the shortest time. And this is known as Fermat's principle in optics. So light travels from one point to another along a path of which the time is minimum. So how do we do this? Well, imagine you have two mediums and the light travels from one to the other. So the angle between to this normal vector is θ1 and the other one is θ2. Now if you see the textbook for diagram to visualize, you'll understand how did this formula come about? Because what they did is they have this line, they take this as their x, this is their distance, and because time is distance over speed, this will be their formula. So what they did is from point A to point B in two mediums. It travels in the first medium in a square root a squared plus x squared over c1, and they travel in the second medium in b squared plus d minus x squared whole thing square root over c2, and then you just add the time up to get the total time, and now you want to optimize this time. And to optimize this time, we just need to differentiate it with respect to x and find the minimum point. And then we realize that the minimum point occurs when this equals to 0, which means the point where we see that the minimum occurs at a point where sine theta 1 over c1 equals to sine theta 2 over c2. So it means that when the graph hits this point has a distance, creates an angle over here of theta 1 and here of theta 2, and they are related by this formula. And so you see how we use differentiation to help us get certain constraints for where our point should be. And this is really the idea of optimization, to find the minimum and maximum values. You can take a look at the example again to re-understand it. But with this, now we can use this idea to apply to other forms of problem, and that's really what we want to do when we are applying things. We got the theorems that we prove in math, we apply to prove theories, and from these theories we use it on questions. So it's just a chain of application. So the angle here is known as Snell's law, and so time is minimized when this occurs, and then you can just solve for x easily with this, like the problem here. Because the sine of theta 1, you just use your trigonometry, you get it in terms of x, and similarly for sine of theta 2. Hope you have understand this, and basically these two questions are just a few types of problems that you can do with optimization. There are much more applications, and you can read all about it on the web or in the textbook. We'll move on to something which requires a bit more technicality, and it's a form of application of differentiation it helps with evaluation of limits. So we know that this does not equals to f of a over g of a, because this becomes a new function, and at that point fa over ga equals to like 0 over 0. And so there is this way of solving this type of limits. And so if you are differentiable, so the first way, we'll take the easy version first before we generalize it further. If you're differentiable, means you're continuous, meaning the limit as x approaches a of fa of fx equals to fa, which equals to 0 in this case. So fa is 0 and ga is 0. Let's say we got these conditions, and g prime a is not 0. Then the limit of fx over gx equals to f prime a over g prime a. And it can be easily proven because you can just minus FA and GA, and because they are both 0, it doesn't matter. Divide them by x over a, which also is not over 0, and then you just prove, and because this limit exists and this limit exists not to be 0, you can write it in this form. And so this gives you a very quick way to evaluate limits of this nature. And this is known as L'Hopital's rule, but the simple version. I hope it's clear how you do it, and I'll move on because we want to really touch base with the more general version. Before we go through the general version of the L'Hopital's rule, we have to go through this thing called the Cauchy mean value theorem because it helps us prove the general version. Suppose you have functions that are continuous on a closed interval and differentiable on its interior, and g prime x is never 0 in the interior. Then there will exist a point within the interval such that f prime c over g prime c equals to fb minus fa over gb minus ga. And really, if you think about it, if your g prime c is always 1, it means gx equals to x plus some constant. Therefore, gb minus ga equals to b plus a minus a over b, which equals to b over a, b minus a. And so you can reduce that to what we got earlier as to the earlier mean value theorem. And hence this Cauchy mean value theorem is really a generalized version. So let's begin with the proof. And we need to first prove that GB minus GA is non-zero. And this means that GA does not equal to GB. And that's quite simple, because if GA equals to GB by Rolle's theorem, there will be a point where the gradient is 0, but here the gradient can never be 0. And then we apply the same trick that we use for the mean value theorem, where we orientate the curve. So the curve now could be looking like this. We want to orientate it so that these 2 points are 0 and equal to each other. And so we just take fx minus this, let's just say coefficient of GA x minus GA plus FA. So the reason why we do this is, if we remember the mean value theorem, what we did is FB minus FA over B minus A, then bracket x minus A. Well, we want this to become B in the same fashion. Now, if we divide by GB minus GA, we want this to be GB minus GA when you sub A and B in respectively. So HA is now 0, HB is also 0, and so there will be a point where H prime C is 0, which implies F prime C equals to this coefficient times G prime C, and since G prime C is never 0, we can divide it over, and hence we've proven F prime C over G prime C is FB minus FA over GB minus GA. And with that, it comes with the 0 over 0 version of the L'Hopital's rule, where now we take the limit, we have the condition that we don't need it to be differentiable. Actually, we do need it to be differentiable, but we don't need it to be, we don't need FA to equals to 0 at the point. Instead, we just need the limit to approach 0. And then we need the limit of f prime x over g prime x to exist, or equals infinity or negative infinity. This really actually just means that f prime over g prime is defined, and f and g are differentiable with g prime never being 0. then we can prove that the limit of f prime of fx over gx is actually the same limit, but now is the limit of f prime over g prime. And the idea is to use the Cauchy mean value theorem, because we know that this side looks like the Cauchy mean value already. And so what we do is we let this side equals to some limit because we know it exists. We want to just prove that this limit is the same. And we take an interval from a to x and see, we know that by the Cauchy mean value theorem there exists this following point for f prime c over g prime c to be equal to fx over gx. And we take it, and as x approaches a from the right, c will then approach a plus 2 because the interval gets closer and closer to a plus. And so the limit of fx over gx of as x approaches a plus will actually equal to the same limit as c approaches a plus of f prime x over g prime x. And similarly for the left hand side. And this exactly just proves it, because now your left hand side and the right hand side have the same limit. And so you are equal to each other. So the limit of x approaches a of f prime x over g prime x is the same limit as x approaches a of fx over gx, which equals to L. And this proves the 0-0 version of the L'Hopital's rule. And you can practice more questions to better familiarize yourself with that. But it just gives you a process for evaluating limits by just keep differentiating. So you know here is 0, here is 0. You just differentiate the top and bottom and evaluate. And if it's still 0, you continue differentiating it until either the numerator or the denominator is not tending to 0. And it's inconclusive if it does not exist or it does not equal to plus minus infinity at any point of time. For example, this function, you can take the differentiation above and below and it's 0. You realize that if you just if you realize that you just divide, it equals to this, which equals to 0. But if you were to use L'Hopital's and differentiate, then this part does not exist or does not equal to plus minus infinity. So it's inconclusive, the limit, and you must use other methods to prove either the limit does not exist or it equals to some other limit. And this L'Hopital's works for limits to infinity and one-sided limit. And lastly, there's still the infinity over infinity form, which means that the limit of fx is either plus minus infinity or the limit of gx is plus minus infinity. The proof of this requires a lot more technical analysis, and so we'll omit it for this basic course. But just know that L'Hopital's work in this form as well, where if this is infinity over infinity, you can also just differentiate to evaluate, such as the following over here. So I've come to the end of application of differentiation. It's really about practicing and applying differentiation to solve different types of problems. And the use of L'Hopital's is very useful in evaluating limits. I'll be moving on to integration in the next videos. I'll catch you around. Thank you.